So you've seen in the three previous talks that shear wave elastography is providing an additional information today to the physician, which is tissue stiffness. This information nicely completes the information circle that is provided by ultrasound device. You have the anatomy that is provided by B mode. You have the flow analysis that is provided by the Doppler modes. And today now you have the stiffness that is provided by the elastography modes. And you see that there is a lot of clinical interest here on this stiffness information. And all the manufacturers today are proposing their own elastography mode. The mode we are proposing, shear wave elastography, has a combination of key advantages compared to the other modes that are the following. First of all, you have an automated stress generation, and this increases reproducibility and gives access to internal organs like prostate or liver that on the talks that you just see. You have access to quantitative imaging in 2D or in 3D, like Dr. Amit showed you. And this is done in real time. So these advantages are possible thanks to our scanner, which is a scanner capable of doing ultrafast imaging. Ultrafast imaging, that means that we are able to compute up to 20,000 images per second of ultrasound images. This is more than 100 times more than the frame rates that you can find on the current ultrasound scanner that you can see on the booth here. Typically, frame rates are on the order of 50 to 100 frame rates. So this allows, as I said, to capture the shear wave propagation and to compute shear wave elastography. Now, the question is, can we, in addition to this mode, can we use ultrafast imaging to rethink what has been done here by the past? And the answer is yes, we can do that. And this is the purpose of my talk, is that if we plug ultrafast imaging on flow analysis, then we end up with a new mode, which is called Ultrafast Doppler, that we are introducing today on our system. So Doppler today is clearly divided in two different modes. You have on the one side color flow imaging, which gives you real-time imaging of flow, and it displays you the mean velocity of the flow per pixel in a color-coded representation. So it's mainly used for detection of flow and for localization of flow abnormalities. On the other side, you have spectral Doppler, which gives you a complete quantitative analysis of the flow properties. But this is restricted to one given location, one sample that you need to position on the image. And this is the kind of spectrum that you obtain. Now, the goal of ultrafast Doppler, one of the goals, is to break this compromise between choosing between imaging or quantification, and to do both at the same time, imaging and quantification, on a single mode and not two different modes. To understand how we do things, a few reminders of how ultrafast imaging works. If you look at conventional acquisition, we are insonifying line-by-line ultrasound beams to compute a full image. We need 200 transmit to compute one image. On the ultrafast side, you send a plane wave, and you have all the information in one shot, and you compute one image with one transmit. So you can, by this way, increase by a factor 100 the frame rate available that you can have on your ultrasound system. The concept of that is very simple, but of course behind that there is the technological constraints that are unique, because you need to acquire and process at the same time all the lines of the image to perform ultrafast imaging. If we look at how things are working for color Doppler modes, well, the conventional color flow imaging is based on this kind of sequence. You shoot around 10 samples along a given line, and then you move on the other lines, etc., and you compute your full image line by line. The number of samples that you have to estimate your mean flow velocity is 10 samples typically, which is very short. On the other side, on the conventional pulse wave Doppler mode, you shoot during a long time along a specific given location. This gives you access to a much longer signal with much more information inside, and this is why you can compute full spectral analysis and having a more in-depth quantification of your flow. But this is restricted to one given location, of course. Now, if we apply the concept of ultrafast imaging to the Doppler acquisition, you see that we are computing for all the pixels during all the acquisition time, and we end up with the same kind of data that we have here for all the pixels of the image. So what we can do with all this information, with all the information gathered by the ultrafast Doppler acquisition. The first thing is that we can increase color flow imaging performance. You can increase sensitivity to improve slow flow detection. You can increase frame rate. Instead of having 10, 20 hertz, you can go up. And you can increase, and a consequence is that you can also increase consistency because all the pixels that you acquired are acquired at the same time. They are synchronous. And this is not the case of conventional, where the first line is acquired way before the last line. So you're increasing consistency of your Doppler information. So first of all, increase color flow imaging performance. Second, perform quantification everywhere. You can select anywhere in the area where you want to do full Doppler analysis, and you compute a spectrum. So here, a bit more details how the mode works. So you are in conventional CFI live, you scan, you locate an area of interest, you launch a ultrafast Doppler acquisition, you press a button, and there is a prospective cine loop that will be acquired and that contains 2 to 4 seconds of Doppler data. This is stored in the system, and you can perform on this data your flow analysis and quantification. This is how it looks. You can review your cine loop. Look at the frame rate you obtain here, 106 hertz. This is 5 to 10 times faster than a conventional color flow cine loop. Then you can stop your cine loop visualization, retrospectively adjust the gain. You look at the gain here that is varying to optimize your image here, your color image. Then you can perform quantification. You place a sample volume here. You can move the sample volume. The spectral data is in real time is calculated and refreshed and displayed here from this sample volume. You adjust your baseline. You adjust your gain. Everything is done retrospectively. You can you put your angle correction, and then you can redo that for a second sample volume, and you see the two spectral data displayed at the same time. So we put this one in the middle of the vessel, for example. We adjust the parameters. We put our angle. And we can do that for a third one. For example, let's put it here at the end of the vessel. And again, all these three parameters are independent, so you can adjust the angle independently and switch between the three. Now you can perform measurements. This is an example, like you can perform a peak velocity measurement. Put your data here. This is true for this kind of measurements, but any classical Doppler measurement is available. You do the measurements of your second spectral data, and of course on the third one. And you obtain on this healthy carotid a very basic result is that the velocity at the center is higher than on the borders, which is not so much interesting, but at least is consistent. Now you can adjust also your wall filter setting to the spectrum, change offline and adjust the best value. And finally, you can recompute your cine loop and look at your cine loop in real time here while you're looking at the spectral Doppler, and you can follow the temporal evolution between the the movie here and the spectral data. We have a nice tool also, which is that if you want, which is the localization, the automatic localization of the frame that contains the peak velocity. So you push a button, the frame that displays the peak velocity is located, and you can re-put your sample volume at the peak location to compute your spectral data. So this is how the mode works. The first thing that we check, of course, is that there is consistency between the classical ultrafast, the classical PW mode and the results that we have obtained with the ultrafast Doppler mode. So we compare that in a flow phantom, and you can see that by measuring the peak systolic velocity and the end-diastolic velocity for different settings, here you have different velocity settings and scale settings, that there is a quasi-perfect correlation between the peak velocity that you do in PW and that you do in ultrafast PW. So this is an important thing, because you can do the classical measurement that you do in vascular, you can do it with this new mode. Here is a first example of a complex flow in a subclavian artery. So you can see here a nice movie acquired at 84 Hertz and two spectral data at two different points that are inverted. So let's see what this increased frame rate can bring us. This is an acquisition in a femoral artery. This is a femoral artery. This is a vein. And you can see that this is a cine loop acquired in conventional CFI. So you can see the frame rate here. We are at 90 Hertz. And you can see the pulse coming back and forth here on the artery. And we have pinched the vein to make some flow appearing here. Now let's look at exactly the same cine loop with ultrafast Doppler. So now you see that things are much more smooth. And one very interesting thing is that just after the peak, you see the negative, the reverse flow appearing here, things that you cannot see in conventional CFI because the frame rate is too low. Here we are at 83 Hertz. So now you have a much better representation of the flow dynamics with ultrafast Doppler. And this is, of course, confirmed when you look at the spectrum, where you see that in addition to the peak, you see the reverse flow here that corresponds to this blue signal here. So there is a much better correlation between the imaging information and the quantitative information here. You can look at that at three different times. For example, we look at this time here, you have the reverse flow here on the artery and some signal on the vessel. This is blue and blue. Now, if you look at a second time here, you still have signal on the vessel in blue, and you have your peak velocity here in the artery. And the last thing here, at this time here, we have no more signal on the artery, on the vessel, sorry, and we have the peak velocity here on the artery. We have also some new visualization tool. We are computing, in addition to the clip itself, where you can see your movie, we have an automatic localization of the peak frame, as I said. So this will help you when you want to look at a stenosis to have automatically the frame where the peak velocity is present. We have a mean image of all the pixels along the clip. And we have what we call a peak hold, meaning this is the maximum velocity that we found at each point during the acquisition. So in a stenosis environment, this is how it looks. So you see here, for example, that the peak frame nicely depicts where the stenosis here and where you have to put your sample volume to document the stenosis. And the peak hold is nicely representing where your turbulence flow is. So this is all this area here, while here it's more conventional. So it could be in a clinical framework, it could be a way to localize where there is turbulence when you have a stenosis to analyze. So a brief summary. What are the ultrafast Doppler features? First, a better visualization and understanding of the fast flow dynamics through an increased frame rate and increased performance of the color flow imaging mode. a fast peak localization tool for you to know where is the peak velocity and where to put your sample volume, and a way to quantify flow everywhere on the image and not choose only a single location. So a few examples of potential clinical benefits of that. So first, a reduction of the examination time, because sometimes it takes a lot of time to locate where the peak velocity is with conventional spectral data. A more accurate and reproducible diagnosis. For example, you could compare in a few seconds the stenotic flow. You could make a comparison between the stenotic flow and the proximal or the distal flow using the same data. So the data is acquired during the same heart cycle, and you don't have to move. Everything is stored, and you grab your data you do your analysis from the same data. And after that, I'm sure we will find much more with more clinical experience. Future of this mode. So today we are proposing it mainly for vascular application. So the workflow and the performance are optimized in this perspective. Tomorrow we will add new tools. For example, the automatic angle correction. Now you can choose your angle correction independently from one sample volume to the other, but you have to do it manually. So this is a first direction, adding new interesting tool to increase the efficiency of the workflow, and then extend to other application through a mode that would be not high frame rate, but more ultra sensitive to increase the capacity of the ultrasound system to detect flows. And I just want to share with you some preliminary work on that we are doing in collaboration with Institut Langevin. So this is a thyroid, with conventional ultrasensitivity. This is research data, so don't bother about the quality of the image. But at least we can see that we are able to detect small vessels with the ultrasensitive mode and the ultrafast Doppler mode compared to conventional. And this is an image of a right brain vascularization. So this is small like this. And you can see with a high-frequency probe all the vascularization of the brain with a very nice sensitivity and resolution. So this is research data that we plan to integrate in our future release. I thank you very much for your attention.